Okay, so are there any issues that we want to go over before we get started from Chapter 2, or questions? Or mm-hmm. So the stem and leaf. Uh-huh. Yeah, I probably would need to look at it exactly, and I probably shouldn't do that in front of the whole class because that would mean going into the grade book. But if you want to talk to me after, we'll look at exactly what you answered and see if I can see anything that would be different, and if I can't, then I'll go back and fix that grade manually. And so you can do that for anything that you have problems about with Course Compass. You know, if you have a question about how it's grading it, let me know, and we'll take a look at it together. So, what are there other questions or comments? Okay, well then we'll go ahead and just start with Chapter 3 then. So chapters 1 and 2 were probably the easiest chapters, and then Chapter 3 we start getting into more math. It's still not a really hard chapter yet, but you will see a lot of math. If you can remember back to Algebra 2, you probably saw a lot of this stuff in Algebra 2. We're going to talk about measures of center and measures of variation, and box plots. So we're going to do mean, median, and mode. We're going to do standard deviation and range, and we're going to find outliers and do box plots, quartiles and box plots. So if you can remember some of that stuff, then you will be much better off. And even if you don't quite remember it, it may seem sort of familiar. So hopefully it won't be too bad. So we start off, the very first section of Chapter 3 is measures of center. So if you can think of one number that would represent an entire distribution the most accurately, what number would you give? 0 for what distribution, though? So you have a data set that has a whole bunch of data in it, a whole bunch of numerical data, and you're only allowed to give one number that will represent that data. And what number might you give? 42, because that's the answer to life, universe, and everything. You would give 7? Respective to the data, what number would you give that might represent the data? The mean? I heard somebody say the mean. That's probably the most popular answer. The mean, which is adding up all of the data values and dividing by the number of data values that you have, is usually a very good representation of a data set, and it's probably the most popular representation of the data set. So we actually have 3 measures of center: the mean, the median, and the mode. The mean is sort of a weighted center, so if you've got extreme values on one end, then the mean will be pulled toward that end. And then the median is the literal center if you order from least to greatest, and then the number that appears in the center of your list is going to be the median value, and then the mode is going to be the value that occurs the most often. You can have a data set that has no mode. If no data value is repeated at all, then we say there's no mode for that data set. You can also have a data set that has several modes. So if you have the most repeated value is repeated 3 times, but you have 4 or 5 values that are repeated 3 times, and they're all tying to be the mode, and so you would have 4 or 5 values that were your mode then, so 4 or 5 modes. Or you most commonly will have one mode, the one value that appears the most often. And here are two different data sets, and we will look at the mean, the median, and the mode of these data sets. So the mean for data set number 1, we add all of the data values together. So 300 plus 300 plus 300 plus 940 plus 300 plus 300 plus 400 plus 300 plus 400 plus 450 plus 800 plus 450 plus 1050. We would add all of those data values together, and then we would divide by the amount of data that we have. So I believe we have 13 data values in this data set number 1. So we would add all these numbers together, and we would divide by 13, and that would give us this 483.85. So all of these data values get added together. That's the sum of the observations. And then we divide by the 13 to get the 483.85. For data set number 2, we would add all of those values together, and we would divide by what? 10, because there are 10 data values here. So we would add these and divide by 10. When we added these, we would probably get 4740, because then if you divide 4740 by 10, you get 474. And then the median is ordering all of these data values from least to greatest. So for data set number 1, we would do 300, 300, 300, let's see, 300, 300. And then that's all the 300s, right? Okay. And then 400, 400. And then 450, 450. And then 800. And then 1050. Okay. And since we have 13 data values, which data value will be the center? Yeah, the seventh data value. So 1, 2, 3, 4, 5, 6, and then the 400. And then on the other side of 400, we have 1, 2, 3, 4, 5, 6 data values. So we have 6 data values on one side and 6 data values on the other, so that 7th data value has to be right in the center. What if we had only had 12 data values? Then we would have had 2, but we only ever have one median, so we would do what with those 2 centered? Average them. We would add them together and divide by 2. And that's what we'll do for that 10 value data set. So let's list it in order. That would be 300, 300, 300, 300, and then 2 400s. Oh, wow, okay. 2 400s. 450, just one, or? Okay, and then 940, 1050. Okay. And so we would, our 2 center ones, because we have 10, would be number 5 and 6, which are these. 1, 2, 3, 4. This is the 5th. This is the 6th. And then we have 1, 2, 3, 4. So we have 4 data values on this side, 4 data values on this side. These 2 are our center data values, so we average them. So 300 plus 400 divided by 2, and that's going to give me 350, which is our median here. And note how 400 was our median for the other data set. Yes, the median is order the data from least to greatest and choose the middle value. And then the mean is average, the average. Add all the data values up and divide by the number of data values. And then the mode is the most frequently occurring one, and that's easy to see. In both of these cases, it is 300. Okay, so in the distribution, when we have right-skewed data, which we talked about last time, and left-skewed data, the skewness tends to affect the mean and the median as well. So if we have right-skewed data, then our mean will actually be pulled more to the right if we have right-skewed data. And then if we have left-skewed data, our mean gets pulled more to the left. Whereas if we have perfectly symmetrical data, our mean and our median will be the same. So the mean actually gets pulled more than the median when we have skewed data and extreme data values. And because the mean gets pulled more, it's less resistant to change, or it is less resistant to change. A resistant measure is not sensitive to extreme data. So the median is less sensitive to extreme data values, so it's more resistant. We call it a resistant measure, whereas the mean is not a resistant measure. So determine the mean and the median of these three data values. Well, what would the mean be? I'm sorry? Yeah, we would add these three together, and so we would get what when we added those together? $90,000, and we divide that by 3, and we would get 30,000. So the average here is 30,000, the mean, and then the median is what? The 32,000. And then on this data set, if we add these together, what will we get? 295, and divide that by 3. We'll get nearly 100,000. What do we get? I'm sorry? $98,000. Okay. And then the median is still 32. So it's not always going to be the case that the median will stay the same, but oftentimes the median will stay the same if you've only changed 1 or 2 data values. So you can have extreme data and the median's not going to be affected, or not going to be nearly as affected as the mean. But the mean was drastically affected by this one very extreme data value. So the mean is not resistant, and the median is resistant. Are there any questions on that? I'm sorry? I was wondering about that because I was thinking, so what did you get? 98,000 something? 323.33? And the 3's probably repeat? Okay. I require that you give me at least 3 significant digits. So if you had said 98,000, 300, that would have been fine. Although usually when we have whole numbers and we have to write the numbers anyway, we're going to write 98,323. But then you could stop there because that would have been 5 significant digits, and you wouldn't need to go on. You could have rounded at that point. And so at some point you're going to have to round some of these numbers anyway, but you could round. The most natural place would be at the integer. It's not always 100% resistant to change, but it's always more resistant than the mean. It's not very resistant. It's kind of like degrees of resistance. So we don't say it's 100% resistant and it's 100% not resistant. But in general, the median is much, much, much more resistant than the mean. You're welcome. Other questions? Okay, so which measures of center should be used? A lot of people were like, why do we have 3 different measures of center? Why not just use the mean every time? Well, the mean is certainly appropriate in most cases, but there are certain situations where the mean is not as appropriate as something else. So if we have test scores, your test scores should represent what you've done in the class. And if you have, let's say you're studying history, and if they give you a test over each century of history of whatever country you're studying, and you've missed a century, but you've done well on all of the others. I mean, some professors would drop a lowest grade, but most professors won't, especially on tests, because that represents your knowledge for the course. And if you've missed a century of history, then you really don't know that material. And so if you studied 5 centuries and you've missed 1 century, and you got 100% on everything else, then it seems fair that you would have an 80% average. And you would want to average that rather than taking the median that would be like 100% or the mode that would be like 100%, because you really don't know 100% of your history. You've missed one big chunk of it. And you still know most of it, and so the mean still represents what you know, but it also represents what you don't know. So in test scores, most of the time you will see the mean used instead of a median or a mode. In salaries, though, particularly if you're looking at different places to live or if you're looking at different companies to work with, you would want to look at the median salary because the median is more resistant to change. So if you have a small company and the CEO of the company, the founder, the owner, makes $1 million a year, but then the next highest salary is $80,000 a year, when it's a small company and you do that drastic difference, it's going to shoot the average salary up way a lot. But if you're not the founder, you're never going to get that salary. So that's kind of skewing the result, and it's not very practical. It's much more practical to shoot for what does the typical employee make, and that's the employee, if you line them up from least to greatest salary, the employee that's right there in the middle, that's the typical employee, the median employee, and that's something very reasonable to shoot for. Also, the same thing if you're looking at salaries for a region, you might, if you looked at Middle Tennessee, we would have to factor the Franklin area in, which is has one of the highest salaries in a huge distance with that county. And so factoring Franklin in probably wouldn't be very fair if we did averages, but then if we did medians, then the Franklin people would be up on the high end and they wouldn't be really affecting things so much. And then if you did types of calculators, so if we surveyed the class and said, what type of calculator do you have? An 83, an 84. I think one student even has an 89. So if we took all of that information, we wouldn't want to average those because there's not an 83 and a half calculator, right? And plus, the 83 is not necessarily less than the 84, in my opinion. I mean, they're kind of different features to them, but one's not necessarily better than the other. Really, I don't even like the 92. I would rather have an 83 or an 84 than the... I think the 83 could too, right? Yeah. Oh. So, it doesn't really make sense to average like model numbers or anything. And so the mode, the most frequent one, would be the one that you'd want to do here. So sample mean is the mean of a sample. So we take a sample set of data, we average all of the data together and we divide, or we add all the data together and we divide by the number of data values in our sample. So we just call it a sample mean to denote that this average is only of a sample and not the entire population. We'll also do populations. They'll have different symbols. For populations, we'll use a funny Greek letter called mu. But the sample mean, we use x bar, and then the individual data values in our sample are going to be x values. And all of this is just really funny notation. The subscript, I think you can even kind of ignore because it just basically says the x sub I is just the 1, 2, 3, 4, 5th data value, the first data value, the second data value. So it's basically the sum. This sigma symbol means sum. So add up all of the data values together and divide by the total. That's all this crazy formula here is saying, is what we already know to compute the mean, add up all of the data values, and divide by the total. N, lowercase n, represents the size of our sample. We'll use uppercase n to denote the size of the population. And so, are there any questions about this formula? We'll see that crazy sigma symbol a lot in this course, and it just means add, capital sigma, and it's a Greek letter too. So here we go with a great big huge table, and certainly we don't need this whole table to compute the sample mean, but we'll do something in the next section called the sample standard deviation that tells us how much the data varies. And this table is like the first step to getting the sample standard deviation. So let's say we have a very small sample set, only 4 data values that are in our sample data, 12, 15, 8, and 10. We want to add these data values together because that's what this is, sum of x. These are the x values, and this is the sum of x. So when we say 12 plus 15 plus 10 plus 8, what do we get? 35? 45? And then the mean is the sum of the data values, which we already know is 45, divided by n. And n in this case is 4. I'm sorry, 11.25, right. So that is our sample mean, 11.25, and we use x bar to denote the sample mean. And then we need a column for all of the x squared values. So what that means is I'm going to take this value and I'm going to square it. So this is 12 squared. That equals 144. And then 15 squared, 225. And then 10 squared is 100. And 8 squared is 64. And then if we add, because this says the sum of x squared, so we're going to add this column, 144, 225, 164 all together, that will give me 533. Thank you. So, are there any questions about how to get these first two columns? And then the next column, we're going to take each data value, x, so that's going to be from this column, because those are our x values, and we're going to subtract x bar. Well, x bar, that's our sample mean. We already know, in this case, it's 11.25. So for this chart, we're going to be subtracting 11.25 each time. That x bar is going to stay the same for all four data values. So we do 12 minus 11.25, and what does that give me? 0.75. And then on the next row, we do 15 minus 11.25, and that will give me 4.75. 3.75? No. 15. Okay. Oh, the previous one. Thank you. And then negative 1.25. And then negative 3.25. Thank you. If we add all of these up together, 0.75, 3.75, negative 1.25, negative 3.25, we will get 0. Should we always get 0? Yes, because we are taking the data values and we're subtracting the mean. Some of them will be more than the mean, some of them will be less than the mean, but on average, they should be equidistant from the mean because the mean is the average of these data values. And here, we're going to want to square the data values. And let me say that if you're squaring on your calculator, a common mistake would be not putting in parentheses for negative values. Because if you put on your calculator negative 1.25 squared and don't put the negative in parentheses with the rest of the number, you'll get a negative number, and that's the wrong answer. So you've got to put parentheses for the negative 1.25 and then squared to get the correct answer, your calculator to give you the correct answer. So when we do 0.75 squared, that will be 0.5625. And then when we do 3.75 squared, that will give me and then in parentheses, negative 1.25, close parentheses, squared. And then again, in parentheses, 3.25 squared. And then this is the sum of x minus x bar. So that means we're going to add this value, this value, this value, and this value together. Okay. This I probably should write it like it is up here. So up here, each of these is x minus x bar quantity squared. So here we're summing up x minus x bar quantity squared. So that means I'm going to add this value, this value, this value, and this value. So for each x value, which is my 12, 15, 10, and 8, I've subtracted x bar, and then the parentheses mean that I do the subtraction first, which I did in this column, and then square it, because parentheses say do me first, and then the next order of operations is to square it, and so then I've squared it, and then adding is one of the last order of operations, so the sum symbol says to add everything. So we add the four values, and we get 27.45. I thought that total sounded off, so. Okay. Okay, that sounds better. Thank you. Are there any other corrections, comments, questions? The hardest part of doing standard deviation is probably doing this chart. Not that the equation part is really easy, but it's probably no more difficult than filling out this chart, in my opinion. You may have a different one. And if you do, share it when we do it. Are we ready to move on? Okay. So, sample standard deviation is this chapter. We're going to talk about measures of variation in this section with the range and the standard deviation. And we start off just talking about sample standard deviation. In the last section, or second to last section, we actually talk about population mean and population standard deviation, which aren't that different once you know how to do it for a sample. The range is just the range of the data values. So you take your largest data value, you subtract your smallest data value, and that's going to give you the range. So maximum data value minus the minimum data value will be your range. And then the sample standard deviation tells you how far the observations are from the sample mean. And until we work with sample standard deviation a good bit, it probably won't mean as much to you. But basically, larger the S is, that's what S represents, sample standard deviation. The larger S is, the more spread out your data is going to be. There's going to be a lot of distance between each data value and the mean. And then the smaller the S is, you're going to have a very tight group of data. So the data is all going to be very close to each other. All of the data values are going to be close to the mean. Here are the formulas. There are two formulas that were given for the sample standard deviation. Note that both of them use S, and really this is going to give you the same answer. So whether we use the top formula or the bottom formula, it's going to give you the same answer. The top formula, if you look at the numerator, does that look familiar? That was, in the chart that we just did, the sum of the fourth column, right? And then on this bottom formula, we have the sum of x squared. Well, that was the sum of the second column, right? And then we have the sum of x. Well, that was the sum of the first column. So this was our second column, this was our first column, and this was our fourth column. So all of these things in the formulas we can get from the table that we just filled out. If we do S for the table that we just filled out, we would have it be the square root of, what was that sum, 26.75? Okay. And then what was our n for the previous data set? 4, because there were 4 data values. So 4 minus 1. And of course, if we're putting this in our calculator all at one time, we're going to want to put parentheses around the denominator to tell our calculator, hey, do this operation first. This is all in the denominator, and then divide. Also, there will need to be a parentheses around the whole thing. So when you write it out in your calculator, you're going to have the square root symbol, and it automatically does an open parentheses when you get the square root symbol. And the reason we have parentheses around the whole thing is to tell it all of it's under the square root, because this whole thing is under the square root. So automatically your calculator will do an open parentheses, and then you'll do 26.75 divided by 4 minus 1, and then close both parentheses, and then enter. And what do you get when you do that? Okay. Are there any questions on that? Is everybody getting, are you getting something different? $26.75 come from? It came from the bottom of this table. So, that's the total of this one. Yeah, okay. Right. I think that the 6th edition of Weiss did not use the eyes, and the 7th edition, which you have, did use the eyes, and so that's why there's a little bit of difference. I think it's less confusing without the eyes. The eyes, like x sub 1, would denote the first data value. So the 12 would be x sub 1, and then x sub 2, subscript, so it's below, x sub 2 would denote this 15, and then x sub 3 would denote the 10. So x sub I just means, that you have subscript. So it means all of the x values. So when it says sum x sub I, it just means sum all of the x values. But I think that for our purposes in a lower level stats class, there's no reason to be so exacting to put the i's there. It would probably have less confusion for you without the i's. Yeah, they're the same equation essentially. Other questions? Okay, and then if we did this bottom formula, the sum of x squared, so this is very much order of operations. When there aren't any parentheses or anything, that's saying that we want to square first, because multiplying, squaring, dividing, that all takes precedence over adding and subtracting. So parentheses trump everything, but multiplying and dividing and square rooting are more important than adding and subtracting. So here, this says square first and then add. And so that means the second column where we squared and then added. And what did we get for that second column? 533. 533. Thank you. And then this one, since there are parentheses, it says do this inside stuff first. And so that means sum all the x values. And the x values, that was our first column, and we summed them at the bottom of the first column, and we got 45. And then we have to square the 45. And then we have to divide by n, which is 4. And then we divide this whole thing by 4 minus 1. Okay, so again, if we're putting it all in our calculator at one time, we're going to put parentheses around the denominator. We're also going to want to put parentheses around the numerator. And then, because everything's under the radical, we want to put parentheses around the whole thing. So square root open one parentheses is automatically open, and then you're going to want to open a second one, write all of this out. You won't have to do parentheses here because order of operations says to go from left to right, but you're going to do multiplying and squaring before you do the subtraction. So square and then divide, and that's the order we want it to do it, and then subtract. So, but we do want parentheses around here so it does all of that before it does this division. and then it will do the 4 minus 1 before it does part of that division, and then close parentheses to get everything under the radical. Are there any questions about the setup on here? The parentheses aren't necessary when we write it like this, but I'm adding them so that you see it in your calculator, because your calculator is all on one line, and it is necessary if you wrote it all on one line so you know where the numerator starts and stops and so forth. Okay, so here is the same data set, and we've really already done S using the defining formula. The defining formula is this top formula, and then the computing formula is the bottom formula. So we haven't done the range, though. What would the range be? How would we find it? I'm sorry? Yeah, it's going, we could organize it first. So 8, 10, 12, 15 from least to greatest. And then our least is the 8, so that's our minimum. And our 15 is the greatest, and that's our maximum. So the range is max minus min, or 15 minus 8, which is 7. Are there any questions on that? Oh, we didn't actually compute this value when we did it. It's the same, and it should be 2.986. And so when we did this one, that was the top one we did, that we got 2.986. And this one we got 2.986, which was easier, the top one. And I'll agree with you there that certainly once you've got your chart, the top formula is the easier one to use because it only involves plugging in one value here. Oops. In the numerator. So we only have to plug in the numerator. Whereas with the bottom formula, you've got to plug in two values, square and divide, and do the parentheses and some extra stuff. So the bottom one's a little more complex. But for the top one, we have to figure out what x bar is, and then we have to subtract x bar from each of the x values, and then we have to square that. So actually getting this column, this fourth column, is more complicated than getting the first column, which is really given to us, and getting the second column, which is simply squaring each of those values. So if you have a data set of 4 values, it's not going to be much different in computing these columns. But if you had 1,000 data values, I would much rather do this formula because I only have to add up the data values themselves and square the data values and then add that. Whereas this column, I would have to compute the average, subtract each data value from the average, and then square it. So that would get really messy with decimals and stuff. This one would be much nicer, especially if you're dealing with integer data. So even though the formula itself is harder, the table work would be easier on this one. So, are there any questions about that so far? Okay. Oh, calculator. So we're going to do this using the calculator. And I forgot to pull up the calculator. So to do this using the calculator, we're going to enter data values. I don't think we've done that yet, have we? So when the calculator gets up, oh, and this is in my way. So we will first enter the data into the calculator. So we want to press Stat and then scroll, or actually edit is what we want to do. So Stat and then Enter. I already have a bunch of data values in my calculator. If your calculator is brand new, you may not have anything in your calculator. But if you do, you can scroll to highlight the L1. So I did the up arrow to highlight the L1. And then you can do second clear and enter to clear the list. So highlight the name of the list, second clear, enter, and that will clear the list. And then we just put 12. So 1, 2, oops, it's a little bit more sensitive than I realized. 1, 2, and then enter, and then 1, 5, enter, 10, 8. So the first steps are stat, edit, and then enter the data into L1. And then we're going to do stat again. We'll scroll till we get to calculate, and then we'll hit option 1 for 1 var stats. And by default, it will do 1 var stats of L1. So stat, and then I'm going to use the right arrow to scroll to calculate, and then 1 is already selected, and that's what I want, 1 var stats, so I'll hit enter, and I could type in second 1. Second 1 will give me L1, or I could just leave it as 1 var stats. That would give me the same thing, because by default 1 var stats will do L1. So that will tell me that the sum of the x values is 45, and that's what we got, remember, for our first column. It will also tell us that x bar is 11.25, and that's what we got. It will tell us that the sum of the x squared values is 533. That's what we got for that second column. And then it will tell us that Sx is 2.986, and that's what we got for using the defining formula and the computing formula when we computed by hand. But the calculator does all of that work for us. If you're told to use the defining formula or the computing formula on homework or on a test, then you'll have to do it by hand. If you are not told, you should use your calculator, because, in my opinion, you should use your calculator, because the calculator is easier and it gives less errors if you actually know how to use it. Even if you are told that you have to do it using the defining formula or the computing formula by hand, you should check using your calculator, because it doesn't take that long to check, and it will tell you whether you've got the right answer or the wrong answer. And it'll give you, these sorts of things in between that might help you know where you went wrong. So you know what the sum of x is, what x bar is, what the sum of x squared is. So it might help you say, oh, that's where I went wrong. I computed the sum of x squared wrong, and mine's different from this. Another thing that I should note, when you put the numbers into the calculator, 12, 15, 10, 8, you should double check them every single time. Because if you make one mistake here, that's the only way really you can get the calculator to mess up, is making a mistake here or not reading the right thing off the calculator. So 12, 15, 10, 8, double check it, and then it's just as easy once you've got that data in there as pressing a couple of buttons and it gives you the answer. Also, be sure that you're doing Sx for the sample standard deviation and not sigma. Sigma is the population standard deviation, and it gives you a slightly different value, and we'll talk about why when we get to doing that. Are there any questions? If I say using the defining formula or the computing formula, you've got to show me the table and then show me the formula with your numbers plugged in, and of course show me the final answer. So those are the three things I'll be looking for, is all the table values and their sums, and then the formula with your numbers plugged in, and then your answer. Other questions? Okay, so like I talked about before, when we have a small standard deviation, then our data is going to be clumped together. When we have a large standard deviation, our data is going to be more spread out. We have most of our data, more than half of our data, is often within one standard deviation of the mean. So if we go out one standard deviation from the mean, we're going to usually have about half or maybe even more than half of our data within that one standard deviation. And then if we go out 2 standard deviations from the mean, we're going to have almost all, the vast majority. And then if we go out 3 standard deviations from the mean, here we have 100% of our data set. Not always will you have 100% of your data set is going to be within 3 standard deviations, but it's very unusual to be outside of 3 standard deviations. So it doesn't happen often at all that you're outside. So it's much rarer to be outside of 3 standard deviations. And it's the same thing down here. Again, notice how most of the data, more than half, is within 1 standard deviation, and then almost all is within 2. And for this case, since we have such a small data set, all of our data is within 3 standard deviations. But that probably wouldn't happen if we had 1,000 data values. We would have a few data values, a handful, outside of the 3 standard deviations. So the more variation you have, the wider the spread is, the larger your standard deviation is going to be. The standard deviation is the most used measure of variation. The range doesn't tell you much. It just tells you the distance between the maximum and the minimum values. But the standard deviation tells you sort of the average distance or the average variation from a data value to the mean. So it tells you kind of what the whole data set is doing rather than just the 2 most extreme values like the range does. It is not resistant to extreme data values, though. So it will be affected when you put in extreme data values. It's probably more resistant than the range, because the range, if you do an extreme data value, since the range is only the measure of extreme data values, it's extraordinarily not resistant, but it's still not very resistant to change. And this is what we were talking about earlier when we said that almost all of our data is going to be within 3 standard deviations. Chebyshev's rule tells us that 89% of our data, no matter what the shape of the distribution. So remember last time we talked about all the different shapes of the distribution. They could be uniform and right skewed and left skewed and J and inverse J and all those different things. Well, Chebyshev's rule says that 89% of our data, no matter what the shape of the distribution, will be within 3 standard deviations of the mean. So if we go out 3 standard deviations, we've got 89% of our data, the vast majority of the data. Only 11% could possibly be outside of that 3 standard deviations. If we have a normal distribution, remember I talked about how special the normal distribution was and how we really liked it as statisticians. If we have a normal bell-shaped distribution, then 99.7%, an astronomically overwhelming majority of our data, will be within 3 standard deviations. So what that's saying is if we had a normal data set and we had 1,000 data values, how many data values would be outside of the 3 standard deviations? 3. 3 of us, or actually 100 if we had, no, it's 1,000 because 997 data values would be within 3 standard deviations, and 3 data values would be outside. So if we had 1,000 data values, only 3 of the 1,000 would be outside of the 3 standard deviations. So to be more than 3 standard deviations away from the mean in a normal data set is extremely atypical, extremely rare. And with Chebyshev's rule, you could have much less than 11% that's outside, but that's the absolute maximum. You'll have 11% outside. You'll have at least 89%, maybe possibly a lot more than 89% within your 3 standard deviations. In the 2 examples we saw, which weren't really normal distributions, they were a little bit skewed, we had 100% of our data within 3 standard deviations. And we'll take a break here and come back and do quartiles.